In this section, we're going to look at Riemann sums and definite integrals. So we're going to move beyond finite sums, which were the rectangles that we had used for Riemann sums, and explore what happens in the limit as the terms become infinitely small and the number of rectangles approaches infinity. Riemann sums here may now contain negative values, meaning some of our graph might be below the x-axis, as well as positive values, giving that the graph is above the x-axis and they can equal to 0. Dealing with negative area, area below the x-axis counts as negative area, and the total area between an interval for some curve is really a net area where the total area below the x-axis is subtracted from the total area above the x-axis. It's important to note that a definite integral is a value, it's a number, while an indefinite integral is a family of functions. This is what we had began integration with, in that we were including a plus c or a constant term at the very end. Make sure that you take a look at the definition of a definite integral as a limit of Riemann sums, and that you also take a look at the definite integral notation. You might have a pop quiz on the parts of a definite integral. But let's start looking at some examples. It's important to note that continuity implies integratability. If a function f is continuous on a closed interval, then the function is integratable on that interval. The definite integral as the area of a region, make sure you take a look at that as well. But let's start with some examples. Sketch the region corresponding to the definite integral, then evaluate each integral using a geometric formula. If we take a look at the first one, they want the integral from 1 to 4 of 3. Well, 3 is just a constant linear function, but if we're going to cut it off on the limits that are given to us, we really now have a rectangle. So to find the area of a rectangle, it's the base times the height. So then this is 3 times 3, which is 9 units squared. If we look at this next one, they want it from 0 to 3, and this is 3, 1, this is 0, 4. Well, now we have a triangle, and they want this area. Not a triangle, it's a trapezoid. What am I talking about? So, to find the area of this, it's 1/2 our height, which is 3, plus our two bases, which are 4 and 1. And that'll, calculating all this, give us 15/2 units squared. If we look at this example, we have a semicircle going from -3 to 3. So we know that the formula for this is pi r squared divided by 2. If our radius here is 3, all we need to do is substitute our values in, which will then give us 9/2 pi units squared. Now, properties of definite integrals. The definition of a definite integral on the function on a closed interval specifies that our lower limit a has to be smaller than our upper limit b. However, it's convenient to extend the definition to cover cases in which a is equal to b or a is greater than b. Let's say that you have a function defined at x equals a, then the integral from a to a, meaning you really haven't gone anywhere, is going to be 0. So the area of one point is just 0 because you really don't have a region there. If f is integratable on a closed function, but our lower limit is above on the integrand, on the integral sign, and our upper limit is on the bottom, then we can simply just pull out a negative and flip the limits and take the integral as usual. Additive interval properties. Let's say that they want the integral from a to b, however c falls somewhere in between, then we can split it up into two integrals, from a to c and then from c to b. In the end, we're really going from a to b because c is right in between both of them. Properties of definite integrals. If you have a constant before your function, simply pull it out and then integrate as usual. Or if you're adding and subtracting two functions within the integral, simply integrate the first part, add or subtract the integral of the second part. So let's look at some examples. Evaluate the given function using each of the following values. Here's our problem, and these are parts of the solution for that problem. Well, if we look at the problem itself, we can split it up into three integrals. Going from 1 to 4 of x squared plus the integral of 1 to 4 of 3x, make sure that you include dx on each of them, plus the integral of 2 dx from 1 to 4. But if you look at some of the solutions that are given to us, well, the integral of 1 to 4 of x squared is 21, plus we've got a constant in front of our function. If we pull it out, we're left with x dx from 1 to 4, which we know will be 15 halves, plus, again, we've got another constant, but then we don't have a function on the inside, which is okay because we have this here. So we have 2 times 3. Multiplying all this out and adding it up gives us a solution of 49.5 units squared. Looking at another example. These are part of the solutions, and the problems are these down here. Well, it's asking us to go from 0 to 5, but we're given 0 to 3 and 3 to 5. All we need to do is add the two. So we're going to take from 0 to 3 of f of x dx plus from 3 to 5 of f of x dx. We know this is 7, plus we know now this is -4, so then that just gives us a solution of 3. If you look at part B, our lower limit is on top and our higher limit is on the bottom. All we need to do is pull out a negative and rewrite it in the correct manner. Well, 3 to 5 is a -4. With the negative that we had pulled out, makes that a +4. And the last example. The graph below consists of line segments and a semicircle. Evaluate each definite integral by using the geometric formulas. I have already calculated it for each of the different parts separately so that it will make going through these examples much faster. From -4 to 2, that would create a triangle, which I got an area of 1. Going from -2 to 0, that creates a fourth of a circle, which I've calculated its area. Same thing going from 0 to 2. And then going from 2 to 6, that's a triangle, which I've calculated the area up here. So then let's get started with these examples. From 0 to 2, which I've already calculated it to be a fourth of a circle, we know that that's going to be a fourth of pi r squared, and r squared in this case is 2. So then 2 and then squared is 4. But keep in mind that this is below the x-axis, so it's going to be negative. So negative pi fourths times 4 is going to give you negative pi. Going from 2 to 6, you've got a triangle here. You use that formula to find the area of a triangle, and that gives us an area of 4. Going from -4 to 0 is taking the triangle area and the fourth of a circle area. Well, going from -4 to 2, I had calculated it to be 1, -1, keep in mind, because it's below the x-axis. From -2 to 0 is a negative pi with another negative because it's below the x-axis. Makes that negative pi, which is what I had, and that would be the solution here. Follow the same idea for parts D, E, F, and G. For H, we're going to call that extra credit. The first person that sends me an email with the correct solution to this will not have to take the quiz on Friday.